Welcome to Part 6 of this week's online lecture. In Part 6 we will continue our discussion of analysis by infrared techniques. So what are the factors affecting group frequencies? Well, it is possible that you might have two functional groups which are near to each other within the molecule, and this can lead to resonance. If they resonate with one another, then that can lead to a shifting of the group frequencies. So say here we've got propanone. We have a carbonyl stretch occurring at roughly 1715 wave numbers if this is isolated in the gas phase. And here we've got an alkene, and we've got a CC double bond, and this will be stretching at roughly 1650 wave numbers. That is a similar frequency to the carbonyl stretch. So if we've got a molecule that has a CC double bond and a carbonyl bond next to each other, the stretching frequencies will be slightly different. The carbonyl stretch will be shifted perhaps down to 1675 wave numbers, and the CC double bond stretch will be shifted down to 1600 wave numbers. The reason why they've gone down is partly because in a larger molecule its reduced mass has increased. But also notice that the difference between the two frequencies has increased from in the isolated molecules to when the groups are next to each other in the same molecule. Another way this can manifest itself would be because of intermolecular interactions. The most common one would be hydrogen bonding. Here is an example of where we've got a phenol molecule and a diethyl ether molecule, and we're getting hydrogen bonding between the oxygen atom in the diethyl ether and the hydrogen atom in the phenol molecule. Now the OH stretch in phenol should be occurring at roughly 3622 wave numbers if it was isolated in the gas phase. But because of this intermolecular interaction, that is the hydrogen bonding, that's going to weaken the OH bond. That interaction is literally pulling electron density out of the bond and making the bond weaker. So the force constant for the bond is reduced, and now the stretching occurs at 3344 wave numbers. So it has dropped by almost 300 wave numbers because you have reduced the strength of the bond through hydrogen bonding. Let's have a look at a different example here. Here is where we've got 2 propanol in the gas phase and 2 propanol in the liquid phase. In the gas phase, of course, the vibrational bands are not broad. They are really quite well defined. However, you can see that they are much broader in the liquid phase, but you can see the frequency has also changed. So here, in the gas phase, we have an OH stretch occurring at around 3600 wave numbers, and so it is quite a nice sharp peak. But in the liquid phase, it has dropped down to 3400 wave numbers or so. Well, we can understand this drop quite easily, because as you go into the liquid phase, the propanol molecules are going to interact with one another, and you're going to get hydrogen bonding setting itself up, and so this is going to drop the frequency of the vibration. And of course, when you've got all these interactions going on, that is going to lead to a broadening of the spectral line. What about 1-butanol in carbon tetrachloride? Well, in fact, we've got a separation of OH frequencies that depends on the environment. We've got 2 frequencies associated with the OH stretch. We've got one here at around about 3600 wave numbers, and we've got one here at around about 3400 wave numbers or so. Well, what is going on? Well, when you're in solution, you have butanol molecules which are indeed interacting with one another because they find themselves close enough to each other for hydrogen bonding. But if it is not too strong, then of course these molecules may become isolated because the carbon tetrachloride solvent itself is not interacting with the butanol. So you're getting a kind of summation. Some butanol molecules, which are essentially isolated, give a sharp spectral feature at frequencies associated with gas phase OH stretches, and then there are butanol molecules which are interacting with one another and hydrogen bonding between them, which leads to a much broader band. So we get a sharp peak in the gas phase here, a broad peak, and at a lower frequency because of intermolecular hydrogen bonding in the liquid phase. But when we have one butanol in a non-polar solvent, like carbon tetrachloride, we are able to resolve both the free butanol molecules and also the hydrogen bonded butanol molecules. We can also see changes in group frequencies if we change state, especially if the molecule is polar. If we look at a molecule like HCl, for instance, and measure the vibrational frequency from the vapor to the liquid state, that is going to lead to a drop in vibrational frequency of 100 wave numbers or so. And if we go from the liquid to the solid phase, it will drop a further 20 wave numbers or so. And again, these changes can be rationalized in terms of intermolecular bonding. So what about the intensities of group vibrational bands then? Well, remember, as I discussed in part 1, the intensity depends on the change in the dipole moment during the vibration. Well, we do expect that something like a carbonyl stretch to be a strong band because it involves a significant change in the dipole moment, as that bond is very polar. Whereas if it was a CC double bond stretching group frequency, the intensity would be rather weak. Well, of course, if the molecule was symmetric, then it wouldn't lead to any change in dipole moment whatsoever, but generally the carbon atoms will be attached to different groups, but the intensity will be much weaker and will show only a weak band. We can also imagine vibrations of ionic crystals, and they in general give rise to very strong absorption bands. Well, this is the end of part 6 of this week's online lecture. Please continue on to part 7.